So maybe this is the circuit. So very quickly, let me know what is the common mode gain over here. For this circuit, what is the common mode gain? Okay, let's go this way. What is the common mode gain over here? If both the sides are identical, right? What will happen to this point, by the way? Is it 0 or not 0? Not 0, right? So resistance offered by this current mirror might be some RSS, let's assume that, or some R0, right? So in that case, what will be the common mode gain? Both the transistors are in parallel, both the resistances are in parallel. So tell me. Yeah.
RD2 by 2
Okay.
in parallel with 2GM2 R02 by 2 divided by whole divided by RSS plus 1 by 2GM.
GM2 is GM1. Okay, so is it correct, or maybe you want to say something like this? Is it correct? Two resistances are in parallel, RO, RO. So RO by 2. Two GMs are in parallel, so 2GM. And this is RD, RD parallel. RD, so RD by 2.
So, so the top में resistance है वो like RSS तो उसमें include होगा जब PO जब हम देख रहे हैं.
Yeah, if you want to, yeah, that you can do.
Like वो कौन
So RO by 2. Then what do you want to? This is what you want to do. Right? Okay, so this is the common mode gain. What about the differential gain? What is the differential gain? Right? We can write down the CMRR as a differential divided by common mode gain. Right? So CMRR will also be like minus, but it is mod of both of them, so it is plus, right? Okay, so this is what we did already. Okay, so now find out the ADIF, ACM and CMRR. Let's go this way. What is the differential gain for this one? Differential gain first. So assume M3 equal to, this is also M3, this is also M1, and looking into this one is RSS. What is the differential gain?
GM1 R01 in parallel with 1 by GM1 or minus 1.
Right? Okay. So here the gain must be GM1 divided by GM3. Right? What about the common mode gain?
R0 1 by 2
R0 1 by 2
into 2GM1
2GM1
into RSS
into RSS
in parallel with 1 by GM3 divided by RSS plus 1 by GM plus 1 by 2 GM.
So 1 by 2 GM3. 1 by 2 GM3.
1 by 2 GM3. Okay. This is good enough for. This is actually still something is into 2 GM, right? GM1 if you want to write. Because here it was not matching the, it was coming resistance divided by something is wrong, or because this quantity makes resistance, this quantity makes gm transconductance, this is resistance, so resistance by resistance becomes gm, acm has to be unitless.
So in that 2GM, there should not be 2GM. And in the denominator, 1 by 2GM.
So 1 or 2, that is fine. So this is resistance gm. Okay. Common mode gain is 2 gm times 1 by 2 gm3 in parallel to r01 by 2, no, gm1 r0 2 gm times rss divided by rss plus 1 by gm 2 gm. It's same. Any mistake I'm making? No. This is resistance, this is also resistance, resistance times
So 2GM. 2GM.
why it is not there. Okay, yeah, that is not going to be there, right? So that is the mistake. So that is the mistake. So input resistance. So this is the correct one, right? So okay. So this is fine. So you can find out CMRR. So can you comment on the previous circuit CMRR and this circuit's CMRR? What do you think? Which CMRR will be higher? This one will higher CMRR. And why is it so? Look, this circuit has poor differential gain, right? Even common mode gain is also poor because numerator is actually lower value than denominator. Denominator is same, but numerator is here. So common mode gain is also poor. Differential gain is also poor. So CMRR has to be poor compared to the previous one, right? Okay. So let's go this way. In this one, what is the differential gain? Pragya, what is differential gain?
Minus GM1 into R0 parallel with R1.
What is common mode gain? Common, yeah.
R0 1 by 2 in parallel with the 2GM1 R0 1 by 2 into RSS.
This has to be RO to be 3, right?
Divided by RSS plus 1 by 2 GM1.
Very good. So CMRR is already there. Okay. There is no problem. Okay, now let's solve this one. Differential gain for this one. A diff. Yeah. 1 by GM1 minus GM1
1 by GM3
1 by GM3
parallel with R1 by 2
R1 by 2
parallel to R1.
Oh, sorry. Right? Because this is actually, you can club them like this. There is a virtual ground here also in this case because it's differential. What about the common mode gain?
One by 2GM3
2 GM3
in parallel with 2 GM1 R naught 1 by 2
2 GM1 1 not 1 by 2
into R naught 5 in
then
R1
you tell me R1
R1 is
if you want I'll keep it.
one
So in a common mode means this potential and this potential both are same, both are Vx, so Vx both are same, so it's shorted. So even if it is like this, because this is one of the question I gave it long back, that instead of this, if let's assume that if it is like this, if it is like this, then also the gain remains, actually just gain will be changed with this will be RO3 RO4, right? So because these two are shorted, these two are at the same potential, these two are at same potential, all four potentials are like this is Vy both are same, Vx are same, so it's shorted. Op-amp does not make any change in the common mode gain, right? So in this case, tell me, so it will be 1 by 2 GM1 plus RO5, right? Okay, so I'm keeping this to you, like sometimes what will happen, it's a mismatch will be there, like here it's RD, the other side is RD plus delta RD, then you can subtract it and you can find out both sides, you can find out the separate gain and you can subtract them. If it is required, you can, like accordingly you can find out, like in this case V in common mode is like this, both are shorted together, but here RD in, so now you can see both the Vx and Vy are not at the same potential, because here RD plus delta RD and this side is RD. So because of that, Vx and Vy are not same, so you have to take it individually and then you have to take the difference of that. That is going to give you the common mode, right? So common mode gain is nothing but V out 2 minus V out 1 divided by V in Cm. Earlier it was both were together, or maybe V out 2 by V in Cm or V out 1 by V in Cm, so you have to take it separately, right? So that you can do it, it's not a, as I was saying, so you can take from both the side you can find out the gain, subtract it, right? So such kind of thing where you are taking the difference divided by common mode, input is common and output is difference, such kind of gain is known as different common mode to differential gain. That name is ACM to DM, which is common mode to differential mode gain. Here input is common mode, however output is not common mode or shorted, they are taking subtraction. So this is subtraction is nothing but difference or the differential mode. So common mode to differential mode, such gain will be known as something different, right? So that is already given in the book, so I'm not going into that. So we also learn that if such kind of things are there where there is a mismatch, earlier we were seeing that if both are identical, then there is no harmonics will be available, right? However, and whatever the common mode noise will be there, it will be removed. But in such case where there is a difference between the elements like transistors or maybe resistances, these differences will actually show you such kind of, you know, such kind of behavior at the output. So common mode noise is not zero in this case, and you can experience the signal to noise ratio and other harmonics, right? So that is what going to happen exactly, because there is no guarantee that this resistance and this resistance will be same, or this GM and this GM will be same, right? So in that way you are going to see some harmonics at the output. So that is what actually this whole exercise is talking about, right? So whenever you are doing this, so in simulations, there are various simulations are available. One simulation is already known to you, the schematic simulation, where when you are designing it, you make sure that everything is fine. There is no problem, right? All the transistors, all the resistors, no problem, because you are these design values and everything is in your hand, right? Everything is in your hand. But there is another simulation which is known as the Monte Carlo. It is also known as statistical mismatch analysis, where there is mismatch between both sides. So this side is not exactly equal to identical to this side. There is some mismatch. With that, how your output is actually behaving. That for that we are doing such kind of simulation. So in this course we are not doing it, but if you want, you can further extend it and you can design your op amp or whatever circuit you are doing for Monte Carlo also, just to check whether it's working under the statistical mismatch or not. If it is not working for almost like something like 10,000 corners or 10,000 runs, then you have to, you know, do something so that it works, right? Anyway, so now this is one more question for you. Let's start with what is the CMRR for this? This circuit has been taken. All these circuits have been taken from Razavi. Now tell me, what is the differential gain? Tell me. GM1.
R1 by 2.
Look here, R1 by 2 will be here. Output is here, right? So it will be 1 by GM5 in shunt with RO7 times GM1 RO1 in shunt with R1 by 2 in shunt with, sorry, multiplied by GM3 RO3, right? Yeah. Divided by common mode gain, that's going to be, oh, I made a mistake, right? RO7 is not there. RO7 is not there, right? That will be here. So in common mode, R1 will not be there. So it's 1 by GM1, 2 GM1 plus RO7. And here, looking at output side, 1 by GM5 in shunt with GM3 RO3 times GM1 RO1 times RO7, right? So that's the CMR. Okay.
So 2 GM or no 7.
Right. Okay. So now this is almost like end of that CMRR. But very important thing is in any amplifier, how much DC potential you can give at the input side or how much output side you can observe the DC output. That is known as the input common mode range or the output common mode range. So input common mode and output common mode. Generally common mode is DC. However, it might be, you know, AC also. It is not always fact that it is always DC, but most of the time, like 99% case, it's DC. And we are talking about how much common mode voltage you can give over here. In this particular amplifier, how much common mode voltage you can give over here. It might be different for all the different amplifiers, right? So that value you need to find out. Somebody can comment on this, how much common mode voltage we can give over here if VDD is equal to 1.8 volt, in your opinion. So that, like, the borderline is actually each of the transistor has to be the saturation mode of operation, right? So each one of them require the VDS set. So VDS set is equal to V over drive voltage also. Some people also writing VOD. Right? So can you tell me what could be the value? Okay, if you do not know, then these are the equations which you are going to follow, and we have to find out. So, so here when we are doing this, we are talking about the common mode DC biased input in this one, just to start with. So everywhere we kept the required VCM, we kept it everywhere. Let's assume that these are the values, right, which we wanted, and we want to find out at the input side, those are the input common mode range, and at the output side, those are the output common mode range. So if somebody wants to find out output common mode range, then it has to be at these points. And input common mode range means this VCM value we need to find out how much VCM value will be available, right, or which we need to apply. Okay, so let's start with the first one is ICMR, input common mode range, which has two quantities, ICM max and ICM mean. ICM is input common mode, one is max range and one is the mean range, right? So you subtract both of them, that means it's going to give you the output common mode range, right? So ICM max and ICM mean, we can find out two way. First of all, if it is input, you need to find out where are the inputs given. So we know that the inputs are given at the common mode side here. If you are going upside, it's a max value, downside, it's a mean value. We need to find out these two voltages, that which are those. Okay. Now, if you are interested in, let's say, downside, right? I am writing everywhere VDS. VDS is exactly equal to VDS set. I'm talking about that one, which is more than 250 millivolt. That voltage I'm talking about. So this transistor minimum require VDS, right, which is 250 millivolt or more than that. This side it's a VGS1 for this one, right? So gate to source potential. So here, if you look at this from this point to this point, can you see two voltages in series? So those are VGS1 plus VDS2, and same is true for this side also. If both sides are identical, if not, then also you can write down that accordingly, right? So VGS1 plus VGS2, that's the ICM mean. Whereas if I'm interested in finding out the max side, look at that from here to here, if it is VDS, and I know that VDS set is nothing but VGS minus VTH. So if this is VGS, this has to be VTH, right? But opposite value, so minus 2 plus. If you look from the top side, you can see here, like excluding VDD, from here to here VDS3, and from here to here it's VTH1. So addition of these two are going to give me VDS3 minus VTH1. However, when we looked at the minimum side, this side was 0 volt. Whereas in this case, it's not 0 volt, it's VDD. So you have to subtract VDD minus this value. That will make the max side, right? So we know the input common mode, mean side and max side. So ICMR, if somebody is asking me, then ICM max minus ICM mean is going to give me the ICMR. ICMR max was VDD VDD minus
VDS3.
VDS3 plus VTH1 minus mean side is
VGS1 plus VDS2.
VGS1 plus VDS2. VGS1 plus VDS2. So, right. So you can keep the exact value, VDD minus VDS3 plus VTH1 minus VGS1 minus VDS1. So this is the input common mode range which you can apply at the input side. Max and mean values are already available to you. So whatever the small tiny range is available, in that region you can apply the voltage. Sometimes you do not have any region of operation like that. So like in this case, now can you comment on if this is 1.8 volt, how much input voltage do you want to apply over here? Common mode voltage. I know that this is more than 250 millivolt. This is again 250 millivolt or more than that. This is 250 millivolt. And VGS1, you know that what is VTH. Do you know your VTH? VTH is, let's say, around 300 millivolt. This is kind of fixed. You have to make the budget that how much voltage do I need at particular node, right? Note that if you are giving here 700 millivolt, then this will become around 900 millivolt. You see? So it's adjustment of the voltages only. It will follow the KVL, right? But here you have enough headroom is available. That's why you can do it. Sometimes what is going to happen? Other things remain same. So there are 1, 2, 3. If VDD is equal to, let's assume that VDD is equal to 0.9 volt. Note that you can each one of them you can keep around 300 millivolt and things are gone, right? So accordingly you have to give the input just to achieve each one of them as, let's say, 300 millivolt. Do you understand what I mean to say? Yes or? So each one of them will be 300 millivolt. So can you find out what should be the value over here? What do you think?
0.6 to 0.6.
Now this situation is very tight. Here it's VTH is also here. Let's say this is 300 millivolt. This is 300 millivolt. So remaining 300 millivolt is here. And you have to make sure that this 300 millivolt is actually VGS minus VTH. Right? So how much VGS do you want to give so that this becomes 300 millivolt?
600.
Around 600 millivolt. If you are giving VGS equal to 600 millivolt, now look at this. This becomes 300 millivolt. There is nothing is left over here. So this transistor went into, out of saturation. Like across this, it might be like 1 or 2 millivolt or picovolt, femtovolt, something will be coming. So this input is very important. In same way, you can find out VBP, VBN, right? Same way you can find out that how much do you want so that here it becomes 300 millivolt. Can you tell me what should be the VBN value so that this will become 300 millivolt? VGS plus VTH, right, at the input side. Sorry, VDS plus VTH at the input side, right? So that one VTH is gone over here, right? And that makes, you see? So it requires at least 600 millivolt, something like that, right? So these are the things you have to work out. Sometimes it will happen that transistor will go out of saturation. If it is 1.8 volt, it's fine. If it is low supply voltage, it's more tricky. It's very difficult to achieve the required gain also, right? So I'm just showing you one of the picture, but I would recommend which technology are you using right now?
28.
And what is the supply voltage?
1 volt.
So then it will be difficult. Okay. So try with that, but it will be difficult. anyway. So just I was showing the picture that what's going to happen and how you are going to make the required common mode. So now the same way you can predict the output common mode voltage also, which is actually coming from OCM max and OCM mean. OCM max is output common mode max and output common mode mean, right? So max side is upside, mean side is downside, and this is quite simple to know that, because here it's VDS2, here it's VDS1, VDS3. I'm keeping it mod just for, because the actually those notations are going up and down, right? So I'm keeping mod so that it's same, right? So you can find out the max side is nothing but VDD minus VDS3 minus VDS1, right? Same way we can find out the mean side is nothing but VDS2, right? And subtracting this is become OCMR, right? So that is the output common mode range, right? That's not difficult. Okay, so common mode range is the one which determines the range of voltage for which every transistor stays in saturation. By the way, what we are doing is we are assuming every transistor is in saturation irrespective of what VDD you are giving. If it is very poor VDD, it's a variable, so it can damage your range, right? And ICMR is an allowable swing at the input side, whereas the OCMR is an allowable swing at the output side. Right? Both are giving you the small range of voltage, which is going around which you can give the answer, right? And these are not the unique answer, as I told you. Look, some people will make VDS equal to, let's say, 300 millivolts. Some people will keep it 250 millivolts. Some people will keep it 370 millivolt, 270 millivolt, or something. Accordingly, the output will change. So everybody will not get the same answer for the same design. By the way, design looks same, but it might be different. So here, each one of the you give here possibly like with VDD by 2 of input common mode, it should work. If it is not working, just you change the input common mode voltage accordingly. This is not the specification, I'm giving you hint just to start with, right? Okay, so now find out ICMR and OCMR for this one. Let's start with the OCMR. OCMR is quite easy, right? What is OCM max? What is OCM max? VDD mod of VDS 5 minus VS, VSD VSD 5. Same, right? Mod, I'm keeping mod, so it's same, right? That is what I told over here also. I'm keeping mod so that here it's actually showing like this, plus and minus. To make it VDS, it has to be minus plus, right? So that's why I'm saying it's mod. So VDS 5 minus VDS 3 minus VDS 1 minus VDS, oh sorry, I have to stop at VDS 3 of itself, right? OCM mean is nothing but other side, which is VDS 7 plus VDS 1, right? Very simple. So at this node, I need at least 500 to 600 millivolts at least I require, so that this will be in saturation, right? Both the transistors are in saturation with 300 millivolts. Hmm? VDS 3. I kept it, right? This is output, right?
ऊपर भी होगा
So I took M5. VDD minus.
V out
आउटपुट
वहाँ
एम
लिखा
फाइव
हुआ
के
है
नीचे
Hmm?
आउटपुट
Oh, okay. Sorry. It's my mistake. I assume that X and Y are the output. Okay, that was the mistake. You're right. So here then we require VDS 3. So I require at least 900 millivolt. For such configuration, 900 millivolt has to be here. But if your VDD is zero point 0.9 volt, then or 1 volt, you can't use it. It will be very tight. You can design it, but it will be very tight. Like even if you keep here 250 millivolt, 250 each one of them, then also like if it is going here to there, then it's gone. You have some margin, right? Then it will work. So if VDD is 1 volt and each one of the transistor has 250 millivolt, it's very tight, right? Does not give you guarantee that slow corner, you know, it will go to maybe one of the transistor will go to let's say 200 millivolt and other is gone, right? That will happen.